My name is Martin Brehm. I'm the developer of the Molecular Dynamics module in ORCA, and I'm happy for the opportunity to present some of the new features here. First, a general note. As you already probably noticed, I'm giving this presentation live. It was not pre-recorded, so I cannot answer your questions in the question and answer panel during the talk. So please be patient. I will answer all of them after my talk. So let's directly start. I just need to move the Zoom bar here a little. Okay. As you probably know, you can quite simply run a molecular dynamics in ORCA. You just need an input as shown here on the left-hand side. You just need to add MD to the simple input line, and you need to specify such an MD section here. This would be a working example. You just initialize the velocities to 300 Kelvin and you run a molecular dynamic for 100 steps. So this input is already sufficient, nothing more to do. Let's briefly discuss the structure. The thing on the left-hand side we call the ORCA input, of course, you know that. And what I call MD input are just the two blue lines here. And in the following of my talk, I will only discuss the MD input. So please don't wonder if you see any ORCA tags. I will only discuss the part which is within the MD section here, because this is what controls the molecular dynamics module. And there is one major difference to the main ORCA input. The MD part is executed as a script, so it is run line by line from the top to the bottom, while the main ORCA input is keyword-based. So the MD thing here is not based on keywords. Why is that the case? It's quite simple. It allows to do complex multi-step simulation protocols. Here you see a simple example. In the beginning, you would initialize the velocities to 300 Kelvin. Then you would run 100 steps at this temperature. Then you would ramp down the temperature from 300 to 100 Kelvin during additional 500 steps. And finally, you would run 1000 steps at the reduced temperature of 100 Kelvin. And you do not need to restart ORCA. So this is all one ORCA run, and this is just the script which you give to the MD module, which is executed from the top to the bottom as a program. If you want to know the details behind it, you can also write complex programs which have nothing to do with molecular dynamics. Here's just an example. Feel free to ignore it. This is a Turing machine emulator, which you can run in ORCA in the molecular dynamics module. This has nothing to do with chemistry. I'm going to skip over this just to show you the power of this input language with which you can define your simulation. Now let's get into the actual features which are new in the molecular dynamics module. The first thing I shall mention is the so-called reference trajectory feature. It means that you already have an existing trajectory with frames and you recompute selected frames of this trajectory. Why would one want to do this? One example would be to compute the energy or properties with different levels of theory. So for example, you have a trajectory from DFT and you want to compute every 100th snapshot then with MP2. And then you can simply put this trajectory into the reference trajectory run and go through it again. And you can also compute the work along a trajectory, so the mechanical work which needs to be employed, which is useful for certain situations. The next thing which we newly implemented here is the so-called wave function extrapolation. As you probably know, in a molecular dynamics simulation, you're doing a lot of steps and there is only very little change between these steps. All the atoms are moving only a tiny bit. And as you can imagine, also the wave function will be almost the same because the displacement is so small. So it would be a good idea to somehow extrapolate from the last n converged wave functions to make a better initial guess for the next step. And this is indeed possible. It exists since quite a long time, and we just implemented it in ORCA now. And you can quite easily switch it on. You can see it here. You just write WFN extrapol ASPC, which stands for Always Stable Predictor Corrector. This is the method. And order 3, you can play with that. It is just the extrapolation order. It will not influence any results, so the trajectory will be exactly the same, but it can save a few SCF cycles. Oh, sorry. So you can use that to slightly reduce the computation time. Yeah. Coming to the next features. Of course, very important in molecular dynamics are thermostats. you need them to keep the temperature constant or to run a simulation in NVT ensemble. What we already have is a very simple Berenson thermostat, the Nose-Hoover chain thermostat, and the stochastic CSVR thermostat. These are already implemented. What I newly added is the so-called Langevin thermostat. And it is a particular interesting kind of thermostat because it works by using two effects, adding random forces to the atoms. So there are random forces acting on all atoms, just dragging them around, and adding a so-called drag force, or in German, Reibungskraft. So as faster an atom moves, the stronger the drag force is. So atoms will be decelerated. So fast-moving atoms will be slow-moving atoms afterwards. And this is interesting because in principle, you can do something like a Brownian dynamics. You can, so this would emulate an effect of an implicit solvent, which is just pushing your atoms around. And you can independently switch on and off the drag force or the random force. Here's an example. If you want the whole Langevin thermostat, you just write this line. And if you want only the drag force or only the random force, you write the line below here. Then you can say you want only a part of this Langevin thermostat. What is not new, but what I shall mention is that the thermostats are compatible with so-called regions. You can define so-called regions in your system, which is just a subgroup of your atoms. It could be a certain type of molecule, or maybe only the left half of your system, whatever you want. You can define these regions by simply specifying atom interval or multiple intervals per region. That's all possible. And you can attach a thermostat per region. And these can be different thermostats and also different temperatures. So for example, you are free to thermostat one molecule kind at a high temperature and at the same time a different molecule kind at a low temperature. Or maybe you can keep the left half of your box at a high temperature and the right half at a low temperature. So you could even study how the heat flows through your system. This is all possible in the ORCA MD module implementation. This is just a simple example. You can have more complicated regions also, of course. Another thing where we added some things is the velocity initialization. Of course, when you want to run a simulation, it is important to have initial velocities, and there are many different approaches how this could be achieved. One thing would be just to start with 0 velocities, so all atoms are resting in the beginning. Of course, this is not very realistic. You would need to heat up your system in the beginning. So what one typically does is starting with random velocities. And these are typically created from the Maxwell-Boltzmann distribution, because this is how in reality the atom velocities are distributed. There is one improvement which we implemented here. Now, these random velocities will not lead to an overall angular momentum in your system. So this means despite you have random velocities, your molecule or your cluster will not rotate. It will be randomly chosen in a way so it's not rotating in the beginning, which is quite convenient, I would say. Other possibilities which already exist are you can initialize the velocities along a selected normal mode if you have computed a Hessian before. So for example, you can start with only one normal mode in motion and you can have a look how the energy diffuses into other normal modes, which would in principle, for example, allow the computation of 2D infrared spectra or so. And what is new? I added features how you can put initial velocity to a linear translation of a molecule. For example, you can stage a collision experiment where two molecules start moving against each other, and at some point in the simulation they will collide. And you can also put initial velocity into the rotation of a molecule. So you can start with a deliberately rotating molecule. Just to show you a few examples how this would work. Here again, we define two regions. In this example, each region contains one molecule. And then we initialize the overall velocities of the total simulation to 300 Kelvin. And then for each of these regions, we additionally give them 100 Kelvin of energy for the rotation of the molecule. And after this rotation keyword here, there's a vector which is the rotation axis. And as you can see here, I chose these two vectors to be opposite of each other. So it means these two molecules would initially rotate in the opposite direction. Of course, this would change during the simulation, then it would just be the initial velocity. Good. One more interesting thing which could be relevant are so-called constraints. A constraint removes a certain degree of freedom from your simulation. For example, if you constrain a bond, this bond can no longer move at all. It is different than a restraint. It means that you really no longer have the bond. It is really fixed, like using a metal bar for this bond. And constraints were already implemented in ORCA MD since very long. But at the moment, you have to add them manually per constraint. If you want to constrain many distances, you would need one such line as shown here on top for each distance, and it can be quite lengthy. What we now implemented is that you can constrain also certain bond types or angle types. Considering the first line here in the lower box, you would constrain all bonds between oxygen and hydrogen. So for example, if you have water, you could automatically constrain all bonds in water, which could be desirable in certain cases. And you can go even further. You can give a star an asterisk for one of the element types, and then you would constrain all bonds from any element to hydrogen. So this would also constrain the NH bond in ammonia, for example. And the same you can do also for angles. You can, for example, constrain all angles which involve hydrogen atoms, as shown here. Now you might ask, how does ORCA know where is a bond? Because of course we don't have to put bonds in a quantum chemical code. There's an automatic bond recognition just based on a distance. So the MD module has tabulated covalent radii and scans your system and tries to find the bonds on its own. And if this is not working, you can also modify these covalent radii. For example, if you have particular cases with particularly long or short bonds, you maybe need to modify these radii, but this is also possible in the input, of course. Otherwise, the bonds will not be correctly detected. Good. Another thing which we newly added, which was, for example, requested in the forum, are modifying atom masses. You might ask, why would one want to modify out atom masses? Because in reality, of course, every element has a certain mass and it is fixed, so there should be no need to modify it. But there are a few examples where this could be useful. One trick employed in molecular dynamics simulation is to replace all hydrogen atoms by deuterium atoms. And what do you gain? Deuterium is heavier and does not move as fast, so also vibrations are slower, and so you can use a longer time step. And with a longer time step, you can simulate more picoseconds per computer time. This is just a trick which is often used. And now with this keyword, you can simply change your masses as you want. Here in the first set mass line, you would set the mass of all hydrogen atoms to 2. And the second line shows that you can, that you can set also the mass of only selected hydrogen atoms. No, selected atoms, no matter if hydrogen or not, in this example to 15. So you can specify any group of atoms by their indices and set them to a given mass. And you can do this as many times as you want because it is executed as a script. So you can also change the masses of your elements multiple times per run and always perform a short run. For example, you could ramp the mass up or down gradually. And if you run the original masses again, you can just put reset and it will put all your masses to the physically correct value again. Yeah. Next thing where we were working a little bit on is so-called collective variables. What is a collective variable? It is just a function which takes the geometry of your system as an input and gives one number as an output. So it is a map from the geometry of your system to a real number. And you can use these, for example, to define restraints or bias potentials or to run a so-called metadynamic simulation. Simple collective variables are distances or angles or dihedral angles. They are implemented in ORCA MD since many years, or also coordination numbers. A new collective variable which are implemented is the radius of gyration. It is interesting because, for example, you can use this to keep a simulation of a liquid droplet spherical. So by pushing this radius of gyration to low values, you would keep a spherical shape. Or in the opposite, if you would restrain the radius of gyration to a high value, you would make this droplet somehow disperse. Here you see an example in the lower part in the ORCA input, you define one call as the radius of gyration for only a selected group of atoms. You can also define a call for the radius of gyration of your whole systems, and you would simply write all here instead of specifying atom numbers. And then you can add a restraint for the call 1, which you just have defined, a harmonic restraint, and you set target to 0 and a spring constant. This means that the radius of gyration of your group of atoms is pushed towards 0, so this means they try to keep a spherical shape, which can be interesting in simulations. Next feature we implemented is a linear combination of existing call. So if you have a certain set of call, you can combine them in any way as you want as a linear combination to get more complex call, for example, reaction coordinates. In this example here, we define two call, which are just distances. The first call is a distance between a single atom and the center of mass of a group of atoms, as defined here. The second call is a distance between two individual atoms. And the third call, which we define here, is a linear combination of the first and the second. And you can put here the coefficients for the linear combination. And in this case, they are simply +1 and -1. So in other words, the third call is just the first call minus the second call. And you can combine as many as you want to get more complex call. And if this flexibility is not enough for your case, you can now even use arbitrary mathematical expressions to define your call, which leads to something like unlimited freedom. Here's one example. We say call type custom, and then there comes a strange syntax, which is the syntax for lambda expressions in this input language. And here you just put any expression you want. For example, in this case, we take the distance between the first two atoms plus the distance between the next two atoms multiplied with a constant plus the sine of an angle of 3 atoms to the square. So here you can write any mathematical expression and it will be a call, and you can, for example, run meta dynamics with it. I think it is a very powerful feature and it allows for arbitrarily complex call. A similar thing we also have for restraints. Until now, we have harmonic and Gaussian restraints, but you can now use arbitrary mathematical expressions to define your constraints. In this example, we define a distance call, and then we add a constraint, which is a sine function of the distance. It is, of course, physical nonsense, because the potential energy of this restraint would go up and down, but you can do it by entering any expression here. Yeah, what else do we have? As I said, the input language of the molecular dynamics module is a real programming language where you can write any program. What is if you don't have enough flexibility with these things? Maybe you want to develop a new time integration algorithm for molecular dynamics, or you want to experiment with a new thermostat, or you just don't trust our algorithms, then you can just write your own molecular dynamics code inside of ORCA. Here's an example. It looks quite strange, but this small script you can use inside the MD section in ORCA, and it runs a normal molecular dynamics, but it does everything on its own. So you do not rely on any of the built-in algorithms. Let's very briefly discuss it. Here in this loop, you run 100 steps of molecular dynamics. This blue part is the velocity valley time integrator. Here you integrate your equations of motion. The green part is the temperature calculation. You just compute the current temperature. Then you print the statistics. The red part here is a Brehm thermostat, which you can modify in this code however you want. And finally, the purple part is the trajectory output. So you have any freedom which you want to implement custom molecular dynamic experiments as you like. Yeah, but you don't need to do this. It is only for advanced users. You don't need to do something like this. That's already all I wanted to show you. Thanks for your attention, and I'm happy to answer your questions now.